is also an awardee for Frontiers of Science Award 2024 in the field of classical and quantum optics. This field is a new field of FSA. His topic, his title is an optical lattice clock with accuracy and stability at the 10 to the minus 18 level. Okay, that's
Thank you very much for the introduction. Yeah, I have this. So it's my great pleasure and great honor to come here to receive the Frontiers of Science Award. Actually, I received this award on behalf of Professor Jun Ye's group in Geelong, CEO Boulder. In fact, as you can guess from the author list, I'm here, and Professor Jun Ye is here. So, but I work in Peking University in Beijing. So Professor Ye asked me to come here to represent the group. Today, I'm going to tell you about how to measure time very, very precisely. And if I say our work, please understand that as mostly Jun Ye's group work at Geelong. And occasionally I'm going to tell you also about some of our my own work at Peking University. Okay. So a famous scientist, Professor Steve Chu, has one saying: the philosophy of his lab is to turn every measurement we can into a frequency measurement, because the frequency measurement is a measurement that we can do most precisely. And here today, today the art of measuring time is a kind of precision measurement. And here I'm going to say, what is a precision measurement? It has two steps. The first step is design or discover an extremely stable system. And then the second step is measuring this system very, very precisely. So here, actually, since I am a child, I'm a big fan of Professor Xintong Yao. And as Professor Yao has put it very eloquently, the spirit of this conference is to seek truth and seek beauty. At the same time, there is still some difference between seeking truth and seeking beauty. And as an experimentalist, I'm going to say, we are mostly here. Experimentalists are here. We are seeking truth more. But as we can see, a lot of you may know that mathematicians came out with the U1 symmetrical gauge theory, and then Professor C.N. Yang and Mills generalized the gauge theory to the non-abelian case of SU2. Then a group of theorists, also Nobel laureate, generalized it to SU3, which constitutes the foundation of the so-called the standard model. But when we come here, these are probably more from the seeking beauty side. And then in the say late 1960s, early 1970s, famous scientists like Heisenberg says, I don't believe there is any new particles, especially heavy particles. But then we have the J-psi discovery, the October Revolution, where Samotin and Richter discovered this very, very heavy 3.1 giga electron particle. It is very, very narrow, and the experiment is very, very difficult. It is as difficult as finding a colored rain out of a heavy rainfall over the whole city. So experimentalists really are saying we have some taste of what is beauty, but we care more about truth. So even if it is temporarily regarded as ugly, as long as it is truth, we are going to move ahead. So how to measure time? The spirit of measure time is actually lies in two basic facts of quantum mechanics. The first is Niels Bohr's certainty principle. The second is Heisenberg's uncertainty principle. So Niels Bohr points out that as the electron moves around a nuclei, it has different orbitals, n equals 1, 2, 3, etc. And then between these orbitals, the energies are different, and the energies are different in a deterministic way. Like say, these energy difference can be characterized by the transition photons. And then, if we want to measure these energy differences, these precise photons, then we have to come into play with Heisenberg's uncertainty principle. If our electron stay on one orbital, on one of the eigenstates, call it the ground state or an excited state, as long as you stay in the eigenstate, then your energy is very, very fixed. But in the measurement, in the process, you have to put the atom into a coherent superposition of the ground state and the excited state in a two-level system in the most case. And if the atom is in a coherent superposition, like illustrated in this figure, which is sometimes called the Bloch sphere, then we can write the coherent superposition in this way: ground state, excited state. Because their energies are different, then you have this phase shift. And the essence of measuring time precisely is lies in how to measure this energy difference, this phase, very, very precisely. So before goes on, I'm also going to talk about time scale. For example, if we have a nuclei and we have a cloud of electrons that oscillate around the nuclei, then we know that such oscillation is extremely fast, like 10 to the minus 15 seconds. If we multiply this extremely fast process by a large factor, say 10 to the 15 seconds, then the period will become on the order of seconds, so a very short period. At the same time, the life of the universe is extremely long, 14 billion years, which is on the order of 10 to the 18 seconds. So a short time scale, a long time scale. If we take the geometric mean of these two, then we get is about 1 minute. So today our work is mainly based on the strontium atoms, which is an alkali earth atom with 2 electrons on the outer shell. So for the strontium atom, the quantum superposition between ground state and the clock excited state has a lifetime of about 2 seconds, 2 minutes. So what happens in the 2 minutes? If you put atoms into a superposition, then it will oscillate with such a short period for two minutes. Then during this time, it will experience 10 to the 17 cycles, which is a lot of cycles. And if we say the pendulum at the period of minute, and then during the lifetime of the universe, it will also have like 10 to the minus 10 to the 17 cycles. So with this understanding, we take the middle point and take the strontium atom to try to build a clock. And when we build a clock, we know that the atoms already have the ground state and excited state, which are extremely stable, energetically stable eigenstates. But when we try to measure this thing, try to measure the energy difference, try to measure the phase, then we encounter the quantum noise. The quantum noise, we can illustrate this as the sphere here, which means when we do the measurement, the superposition either collapse onto ground state or collapse onto excited state with a certain probability. So this kind of probabilistic process will lead to the standard quantum noise, and the typical strontium atom has a coherence time of 2 minutes. So if we have a bunch of atoms here, each atom behaves as a pendulum, and they swing together. Then as we as we measure the quantum noise, if the quantum noise of each pendulum does not affect the quantum noise of another pendulum, then we say they are independent. Then the standard quantum limit tells us the number of measurements, n is the number of measurements, or you can say it's the number of particles, number of atoms, square root of n, 1 over square root of n. So this also happens if we flip the coins in a classical process. But can we do better? In principle, yes, we can do better, which happens if we can control the collective behavior of the atom. For example, if we have n particles, but the the noise of n particles are actually correlated. N particle, if they only have one copy of noise, then you can greatly reduce the quantum noise of the process. We actually call this kind of noise as a entangled state, and here the corresponding quantum noise is called squeezed. So whenever we can have this kind of interesting correlation that leads to the reduction of quantum noise, then we say we can unleash the force of quantum mechanics. So when we can do this, then we no longer have the traditional standard quantum limit of 1 over square root of n. We have actually 1 over n, which is much better. Okay. Today, by discussing the art of measuring the time, if you can take one thing from my talk, that would be to expand the scale of quantum coherence. The coherence comes from when I say the coherent superposition of ground state and excited state. But in nature, there are actually lots and lots of processes that can destroy the coherence. And when I say expanding the scale, I'm not only talking about the spatial scale, I'm also talking about the temporal scale and even the scale inside the frequency domain. So for example, for the external degrees of freedom, like the motional degrees of freedom, if we do nothing to the normal atoms and molecules, they actually move around very fast, um, like here. And even though quantum mechanics says the atoms may behave like waves, however, the thermal de Broglie wavelength will be very, very short. But then, if we can cool the atom down to nanokelvin, say hundreds of nanokelvin or even tens of nanokelvin, then these thermal de Broglie wavelengths will become longer and longer and longer, and then they will collapse into one giant quantum wave function, which is which some of you might know is the Bose-Einstein condensate. At the same time, there are internal degrees of freedom. For example, we can say the spin, which can be either a real nuclear spin or a pseudo spin representing the ground and excited state. So if we have n particles and if they reach such a state that if one particle is found to be spin up, then all the particles must be spin up. If one is found to be spin down, then all the particles must be spin down. Then this is a highly entangled state, which is very good for quantum for the quantum measurement. And all these belong to the same spirit of expanding the scale of quantum coherence. So the quantum coherence, when we can reach a high degree of quantum coherence, then we can use that to build a clock. Specifically, for the strontium atoms we have a pendulum which can swing for over 10 to the 17 cycles before it stops, before it damps down. And we can also have lots of atoms, and then in the end, we can try to unleash the power of quantum optimization, quantum correlation, and so on. So with this, I would like to show the recent progress of the atomic clock. For example, since the late 1960s, these are the atomic fountains, which is the current definition of the second and third. So they are improved continuously along this line to the level of 10 to the minus 16. But then, since the beginning of, uh, actually not only the beginning, since the late 1990s until the beginning of the new century, here uh, we have the iron clock, we have the neutral atom strontium clock and ytterbium clock. These are going down to the 10⁻18 regime, where our 2014 paper, the award paper, goes to 6 times 10⁻18 level, which goes to the 10⁻18 level for both the precision and the accuracy for the first time for all the atomic clocks. So we can do this with neutral atom clock, partially because we have a combination of all these necessary factors, which I'm going to go into details later. So a few years ago in Junye's group, the precision goes to 3 times 10⁻19, and the accuracy is on the order of 10⁻18, small number. And then in a few years, the latest result is actually the accuracy, which is the total uncertainty, goes to 8 times 10⁻19, and then the precision, which is another word of saying stability, actually is much improved by another 50 fold. And the process is actually still going on without hitting a hard wall. Yes. Okay, that's a very good question. Actually, I have one slide about the precision. Precision. So in short, precision means when I hit the target, I always hit, for example, ring 3, which is not very good, but every time I hit ring 3. This is precision. Accuracy means it's scattered around, but the average is ring 10. So okay, you have some impression about having the clock made of the best atoms, which is the strontium, nature's high quality factor oscillator. But here I'm going to say another thing. Probing the most stable atoms actually calls for the most stable laser, which is like a car. The strontium is like nature's high quality oscillator, the best car. If you want to make good use of the best car, then you cannot use bad oil. You cannot use the second good oil. You have to use the best gasoline. So the best gasoline actually corresponds to the most stable laser. I'm going to make another example. So when I say you make or choose or discover something really stable, and then at the second step you measure it very precisely. So let's imagine you already have the really stable thing, which is the atoms. Then it is not guaranteed you can measure it precisely. For example, the mountain is there, so but I cannot see it from my office. I use the telescope, then all of a sudden I can see the fine structure. Then I increase the magnification. Wow, I can even see the finer structure. So this is my own experience in the office. And then there is one night I used my Huawei mobile phone to look at the moon, and this is what I see: almost nothing, maybe a little bit of inhomogeneity. But then if I carry my my telescope and then put my mobile phone into the eyepiece, then you see this: the same moon, different kinds of measurement, different results, different signal to noise. So compared to science, it is the same thing. If we have a laser that is not so stable, then you compare it to you can imagine an absolute time, and this is your atomic clock. Then the first time on day one, your clock is 5 seconds faster. On day 2, 1 second faster. On day 3, 4 seconds lower. If you have something like this, then we call this clock, such a clock is not precise. But then, if you measure something like this, every day you have 5 seconds faster than absolute, than the ideal time. Then we can say your clock is really, really precise, but not accurate. If you have an absolute time, then you have day 1, 0, day 2, 0, 0, 0. Then you say this clock is both precise and accurate. Okay, so having a laser that is not so stable is like measuring a line profile with bad signal to noise. And having a good laser, you can have a much higher signal to noise. And we all know that if you have infinite signal to noise, even with 7 points, you can fit a sinusoidal curve to machine precision. So this is something towards that precision, that direction, which means if your laser stability is improved by a factor of 10, you can save the measurement time by a factor of 100, which is really, really appreciable. For example, we know that if we move an atom higher or lower by 10 centimeters, then the speed for the clock ticking will be different by say 10 to the minus 17. Then if you use the old not so good laser, then it'll take several days. If you use a better laser, then it can only take 10 minutes. You go out for coffee and come back, and then the measurement is done. So it's very, very different. So now we see the importance of having a very, very stable laser. How do we do that? Let's start from here. This is the continuous spectrum of electromagnetic wave, and we are here. We are in the visible light regime, and like say 698 red light. So if we are here, but the natural frequency is like on the order of 10 to the 15 hertz, which is really, really high. If we have a laser diode, which is the first step, just a laser diode, then it will have a line width of say hundreds of megahertz, which is zooming in from the 10 to the 15 hertz, zooming in by a million times. But this is still not enough. So starting from the early 1980s, Professor Zhang Hao, who is my academic grandfather. So this is one of his auto-stable cavities. If we use this to lock a laser diode onto this cavity, then we can reach a line width of about a kilohertz, somewhere there. And now the best laser is actually based on cryogenic silicon cavity, which can have a line width below 10 millihertz, which is the third time we zoom in by a million times. So this is actually our precise tool for providing the oil for the best car to interrogate the clock transition of the strontium atom. Okay, how stable it is? The coherence time is actually about 100 seconds, which means if you go back and forth between the Earth and the Moon by 50 cycles, you can still retain the coherence. The interference fringe won't disappear. Hopefully, in the next 5 to 15 years, we can further extend the coherence time, say to several hundred seconds. Then, if that can be done, we can really say we can extend coherence to one astronomical unit by shining the light between the Earth and the Sun. That will be truly exciting, and will be useful for the interspace measurement and interspace precision measurement. But not only that, sometimes we need to compare clocks with different resonance frequency. Then we not only need one set of ultra stable laser, we need hundreds, a thousand, or even 1 million ultra stable laser at the same time, all with phase coherence with each other. So how do we do that? It actually has to do with the coherent manipulation of femtosecond laser. So if you have a train period, a train of pulses which is continuously phase evolving in time, then in frequency space you will have a forest of lines. But these forest of lines, each of them actually are coherent with respect to each other. So here, this is actually if you have this kind of apparatus, which is called a frequency cone, optical frequency cone, then you can actually bridge the large difference between laser frequency and microwave frequency, and then you can have a whole spectrum of um, of highly stable electromagnetic sources, and this actually leads to half of the 2005 Nobel Prize to these two gentlemen, Jan Hao and Ted Hans. So okay, we have a tour on the optical side. So what about the best car, the atom side? The atom actually has its own problem, but fortunately, generation of physicists have come up with very clever ideas that are implemented to solve the problem. For example, one problem is that atoms that move around. When atoms that move around, according to Einstein, a moving clock ticks differently from a clock that stands still. So if you have these atoms that move around, then these atoms, this clock will behave like this, which looks terrible, right? So how do we do that? So Professor Zhang Hao, when a few tens of years ago, he used to tell Professor Jun Ye as a grad student, so whenever you improve the optical coherence, you will solve the problem. But now we need something more than improving optical coherence. We need to cool the atoms. So just like this, atoms that move around, you shine the laser, then atoms are not only slowed down but also cooled. So they are trapped in both the arc space and the momentum space. So because of the laser cooling and trapping, these three gentlemen, Cohen Tanucci and Bill Phillips, they won the Nobel Prize in 1997. After this, it became apparent that with laser cooling, you can not only trap more atoms, but also you can have more atoms to measure for longer time, which is really helpful for measurement science. Not only that, shortly after the discovery of laser cooling, people developed further techniques for improving the temperature from microkelvin to 100 nanokelvin, this level. So these three gentlemen, Eric Cornell, Wolfgang Pauli, and Carl Wieman, they won the Nobel Prize in 2001. This is where I entered college, and this is where Professor Junye starts his own group as a young professor. But we need another hero who achieved the cooling of fermions into the degenerate regime. So Professor Deborah Jin is the hero of Junye, also of course she's also my hero. We know that fermions, indistinguishable fermions, they repel each other based on Pauli's exclusion principle. So they will occupy different states according to the energy, and this is the Fermi field. So if fermions occupy states like this, then it's less likely they interact with each other, and it is such weakly interacting or even non-interacting fermion that we use to reach an optical atomic clock. And also, in the beginning of this century, Professor Dan Wineland at NIST started to develop his uh, the first ion, the first trapped ion system, and use it to oh, I'm sorry, to use trapped ion system to develop the first optical ion clock, like this, the mercury clock. And then also, he during this process, Wineland developed those techniques to coherently control all degrees of freedom in the single particle regime. So when Junye started his own group as a young scientist, he decided to do something different. How different? Instead of using one single ion, he decided to use many atoms. Of course, many atoms need to be neutral and have long coherence time. So so this gentleman asked him, he developed in last century a very powerful technique called optical tweezer, which means if you shine a strong laser beam onto the atoms, you can actually hold onto the atoms, just like I hold the laser pointer here. But a normal optical tweezer is not enough because it will have distort the energy level of the um, excited state and the ground state in a different way. So in this way, um, if you have such situation, then what you measure does not correspond to the resonance frequency you want to measure, which is bad. And then so these three gentlemen, they come up with an idea to really find a magical wavelength such that when I apply the optical tweezer or magic wavelength optical lattice, the excited state and ground state, they feel exactly the same potential. In this way, what you measure in a trapped atom, it equals exactly to what the atom will have the transition frequency as if they are not trapped. So this is really wonderful. Um, uh, Even though atoms are inside the trap, it has the vibrational level, but we can concentrate on the carrier. As for the sideband, it corresponds to the weak contribution for atoms that change its motional degrees of freedom. For example, this is the blue band, this is the red band. Here, because the finite temperature, we still have some red sideband, but as we lower the temperature even further, this red sideband will be completely eliminated. So it is time to scale up the quantum clock. For example, we can have the degenerate Fermi gas of strontium atoms. For example, we can put almost 1 million atoms onto a 3D crystal here, and enjoying the coherence time of about 2 minutes. Then of course we can encounter different problems. For example, atoms can interact with each other and so on. But if we became a little bit more clever, then every time we encounter a technical problem, we can always convert the technical problem into an opportunity to better control or control the atom in a new way. So these are actually all interesting topics for study, for basic studies. Okay, so how well does our clock perform? it actually performs really well. For example, we can we can have a cloud of atoms and shoot two areas, 1 and 2, and study the difference of these two. So each atom here again behaves like a pendulum. And if we wait for a very short time, then we can see that if one pendulum is in the ground state, all the other pendulum here is also in the ground state, or they are all in the excited state. So they are only in phase with each other. Then if we wait for longer, slightly longer, it becomes the ellipse, or you wait for much longer, um, it can become circular. So which means as time goes on, the resonance, the clock frequency of these atoms and these atoms are actually they have difference, and we can see the difference through our measurement. It's amazing that the coherence time is approaching the natural lifetime of 2 minutes. So as we can see that we all know that you measure for longer, your results can be better. Indeed, we measure for 10 to the 5 seconds, which is about a fraction of a day. Then our precision actually can go down from 10 to the minus 18 to 10 to the minus 20. And actually, this is a continuously improving process. Here, just March this year, we improved this by another factor of 3 to 4. Then, in the same time, with the same measurement time, then you can go to the regime of 10 to the minus 21, which is the present record. With this, I would like to show a comic graph, which is like saying, oh well, the time is stopped. What does that mean? It means in different positions of the atomic sample, then your clock is ticking differently. Of course, with our present precision, we are still not able to distinguish atoms that are microns apart. But suppose 5 years later, 10 years later, if we can really distinguish the resonance frequency of atoms that are just 1 micron away, then it'll provide a really interesting interplay between the effect of gravity and the effect of quantum mechanics, which is exciting. So clock can be our microscope and telescope. So instead of building a large hadron collider or even the LIGO with kilometer arm, we can actually continuously improve our precision and put two clocks which are not so far apart, but still are different enough within our precision to detect interesting physics, important fundamental topics like gravitational waves or even dark matter. In fact, we can put highly precise clocks onto satellites, which is the near goal. Not fully accomplished, but well within the process, say in the grand program in China. So once these clocks are here, they can not only help to detect precisely the very tiny effects on the Earth, but can also help for the detection of the dark matter in space. And I would also like to say a little bit words on precision measurement. So when we turn the precision measurement tool upside down, it also means precision control. For example, if you have a high resolution imaging, then you turn it upside down, shine a parallel light through the objective, then you can focus the light very, very tightly on one atom without affecting the atom in its neighbor. So the same way, if you can distinguish this peak in frequency domain really, really well, resolve all the peaks, then what you can do is the following. You have a bunch of dim states, then you can shine near resonance light onto these two states and move them apart through blue shift of by the laser, then you can have a highly isolated built-in system, which can be really useful in some aspects. So here are one recent work based on the precise spin manipulation we showed in the last slide. We are able to reach topological fermions uh, based on the precision spectroscopic manipulation using uh, using an ultra stable laser. Here, the topological material can reach high topological quantum number like Chen number up to plus and minus 2. So at the same time, in my lab at Peking University, we are also trying very hard to make the next generation ultra stable laser towards the 10 to the minus 17 frequency stability. And here are some recent data. And Zhang is the leading student in this project. He's also here. In fact, many of my students are here. Thank you. So how to proceed? I probably have 3 minutes left. I'm just going to be a little bit quicker to tell you about two directions that we can make improvement. The first is to go deeper in spin entanglement but in state-of-the-art clock. For example, these three gentlemen won the Nobel Prize for reaching quantum entanglement in the photonic side. And here in MIT, for example, in the Volatic group, they put atoms into a cavity, which means atoms behave collectively. If you shine a light to probe the atoms, you actually do not know which atoms are interacting with the light. You lose the information, but which is good because if you have all the information, you will destroy all the quantum coherence and have the full quantum noise. If you don't have the full knowledge, then you can actually save some quantum coherence and reach a better performance than the standard quantum limit. So the black one shows about 3 dB improvement over the standard quantum limit, which is not so large at the present, but it is a really exciting starting point for us to um, further unleash the power of quantum mechanics and quantum entanglement. So another method is, of course, to build a different clock. As you can see, at Gila and in East Boulder, we have different clocks, strontium clock, aluminum ion clock, and ytterbium clock, and so on. All of these can be compared with each other to relatively high precision. But not only that, what we want to say is, if you think about the history of going from the microwave clock, which is like this, to the optical clock with frequencies 100,000 times larger, then a natural way is to say, let's go to even higher frequencies, which is actually the nuclear clock. For example, the thorium nuclear clock. Very recently, we have an archive work. So we have measured the thorium nuclear transition frequency to the kilohertz level and have performed the first comparison between a nuclear clock and between a nuclear clock system and a strontium clock system. I view this as a very exciting starting point for going beyond the already very precise strontium clock. So with this, I would like to thank the GILA strontium 1 clock group, strontium 2, which is the 3D crystal strontium clock group, and then the squeezed clock group and the ultra stable laser group. Long-time collaborator Anna Maria Ray, and also, of course, the nuclear clock group, especially Chuan Kun, who spent 7 to 8 years to really set up the whole nuclear clock setup. So the above acknowledgement is done for Professor Jun Ye. For myself, I would also like to thank my own group in Peking University who has done um, uh, also very hard work and have, have have generated some beautiful results. Especially, I would like to thank my postdoc advisor Jun Ye and also my PhD advisor Chen Xin, who are like family members to me. Finally, I would like to thank my family members, especially my wife Yunju, who have accompanied me through the difficult times. And I want to thank you for uh, for firm trust, constant love, and tremendous support. And in the end, thank you very much.
John, for the wonderful talk, are there any questions?
Uh, it's actually like this. So uh, like LIGO, it's actually a combination between large apparatus like with kilometer arm with the state of the art ultra stable laser. For us, we don't have. For us, we are talking about uh, the much smaller apparatus that can put into say half of this room. But if we can, but uh, if we continuously improve the precision, then even if two ensembles of atoms are only separated by this far, we hope to use the frequency difference or all the difference between frequency distributions and so on to sense the distortion of space by gravity. Uh, yes. Okay. It's like this. So the time scale is to say, in the ideal case, you finish one measurement, then at the most it can last for 2 minutes. But the atoms are actually can remain stable. Even if we don't measure it, it remains stable. The 2 minutes only limits the measurement time. So if we repeat the 2 minutes measurement, 2 minutes measurement, we can go to higher precision. That's right. We probably can do modulation during this process to make it faster or slower. Oh, um, that's I have to say that's that's out of my apparatus. But I can, if you are interested, you can see the paper uh, by the collaboration between Junye and Misha Lukin at Harvard. So around 2016, they have a few papers, a few PRL, PRD papers on this. I remember roughly it is like this. So if we have the cryogenic silicon cavity, which is not only really stable, but also really linear, then if you in the future, of course, um, put such put such system into space, then um, use for example nonlinearity of the silicon cavity to sense some abnormal behavior, um, which is probably model dependent, but I believe if the precision continuously improves, uh, we we should be able to start to make contributions. Yes. Yes. Oh, thank you. So that's actually a very good question. Why we only measure this to kilohertz level? It is actually not limited by the nuclear clock itself. It is right now it's actually limited by the laser part. When I say laser, I should actually say like really short length, short wavelength laser, say below 100 nanometer. Um, so, well, around 100 nanometer. Um, so it is indeed really challenging to extend the really high coherence in the visible light regime into the short wavelength regime. But Professor Junye in the last say 15 years have done some work in the EUV or even EUV, XUV, or even VUV regime on the short side. So it is an ongoing story. Okay, thank you. Um, let's say the first question. Sorry, please say the first question again. Ah, okay. Yeah. Thank you. Thank you. It's like this. In principle, if we have the same signal to noise, then it shouldn't matter whether you use optical clock or microwave clock. However, such microwave clock is actually microwave fountain clock, which means you throw an atom up and then it drops down. In this process, you measure twice. So you really cannot let the atom um, fly for really long. Otherwise you will have otherwise you will have something like this. So you will have almost no atoms to measure, and you also cannot measure for very long. So for the microwave fountain clock, it's the same thing. At most you can have say you can wait for 1 second before before the cloud expands substantially. Then with normal laser size, then your signal to noise will decrease a lot. But the so-called optical lattice clock, you actually hold the atoms in place. Your your shining your clock laser is unable to disturb the atoms out of the optical lattice, so you can measure for very long. That's the difference. Oh, yeah, we use the so uh it's a little bit related to your first question, uh, which means sometimes our interrogation time, the measurement time, can be limited by something else, not ultimately by the inverse of your language. So if you are limited by something else, then you are done. Um, so which means in Chinese, I would say 我们都知道有一个词叫夜长梦多。那么夜长梦多就是说okay, you have to you always want to finish the measurement in as short time as possible. Then if you have higher frequency, which means shorter wavelengths, then you can then you even if your signal to noise remains the same, then you can finish the whole thing in a much shorter time. Um, then your the effect of the noise is generally better. Yeah, yeah. Okay, I know your second question. So I would say it really depends on the decades and decades of technological accumulation. For example, Junye, Professor Junye, the advisor who won the Nobel Prize in 2005, Professor Zhang Hao, he had a dream of building a Hertz laser, a Hertz level line width laser, uh, starting from 1980s. So 1980, the year of 1980. Then after almost 20 years, this dream is accomplished. But but uh, but then after 5 years, he won the Nobel Prize and started to retire. But Junye really uh, take on this task and move on by another factor of 1,000 or more. So into the below 10 millihertz regime. Without such accumulation, you can build a clock, but if you don't have the laser, your clock may have the potential to enable really precise measurement, but you don't have the tool. So you have the first step, having a really stable system. You don't have the second step, having a precise measurement tool to unleash the force. Yes. In what technology? Uh, I would say right now, uh, yes and no. So I say yes if you really realize the intrinsically entangled clock, say you can reach 10 dB squeezing from the beginning, then your clock will win from the beginning. But at the same time, right now we are not there yet. So the clock squeezing I show you is not comparable to the best performance of the unsqueezed clock for the non-squeezed clock. So right now we are still developing the ultra stable laser to the better precision and also increase the number of atoms to accordingly increase in the quantum projection stability. So so we have not encountered a hard wall there yet. If we encounter a hard wall, then the more quantum trick will definitely play a stronger role. But you are definitely right that we are still in the kindergarten a stage of playing with quantum entanglement, especially in the regime of quantum precision measurement. There are lots and lots of things we do. For example, if you can use the GHZ state to do the clock measurement, that will be very wonderful.